Yeah, Dr. Taiban, is it audible to you?
Dr. Taiwan, hello.
Can you unmute and speak?
Now can you hear me? Am I audible?
We can
Yeah,
hear
we
you.
can hear
Okay,
you.
okay.
Yes.
Yeah.
You can start your video.
Okay, I'll just share my screen. Is the screen visible now?
Okay. It's visible,
Yeah,
visible.
it's
Okay.
visible.
Hmm.
Okay, shall we start our program?
Yeah.
I think it's almost 3 o'clock. We will start. Our dear participant and respected speaker, Dr. T. Watham, Taibang Watham. So good afternoon to everyone. This is the last session of our 3 days webinar. I request Dr. Saraj Kumar Patnaik, organizing secretary of this 3 days program. He will propose this welcome. Yeah, Dr.
Okay, good afternoon to all. My dear participants and our research person, Dr. Taibang Watham. He is scientist and engineer SD in the Indian Institute of Remote Sensing, which is an institute under the ISRO in Dehradun. So I am just going through his brief biodata. He graduated from NERIST. So we are fortunate to get him as a speaker here because you see NERIST is just near to us, Pasighat. So it is near to Itanagar, Arunachal Pradesh. So we are proud that he is a scientist there. So now we can hear you from him. So he has completed his MSc Forestry from Mizoram University, Mizoram. And he got his PhD in Forest Ecology and Environment from FRI, ICFRI Dehradun. So he has some expertise that is carbon flux measurement and modeling, forest biomass and carbon estimation. He has experience because he's starting his career. I think so. He has a lot of experience also in this application of geospatial technology in forestry, and also he has worked with the Wildlife Institute of India, and he has a lot of publications, more than 14 research publications to his credit. So we are fortunate to get him as a speaker for today's last session of our webinar. So I think our students, the scientists and some faculties which are now participating will get a lot of information from me. Dr. Taibang, you please start. You are most welcome to this session, please.
Okay, thank you very much, Patnaik sir. And I would like to thank my HOD, Dr. Hitendra Padalia, for giving me the opportunity to interact with the students of this CAU Pasigat. I have made my presentation more towards oriented to do the students, thinking like it will be mostly the students participants, but till now what I see is only 8. So let's see like how much information that I have learned, like through my experience I can share with the participants. So today what I'll do is I'll give the overview of different application, uh, how remote sensing and GIS can be used in field of forestry as well as in terms of ecology. So in this line, we will start with the little basics, like how we can just use the remote sensing data in order to understand our ecosystem or a forest. So the first things that we can see easily from any remote sensing satellite is the, like, when we talk about forest, like forest generally being a very uh, okay, sorry, just so for us, like we can just from the image itself we can understand whether there is any changes that has take place over the forest ecosystem or not. How much forest loss or how much forest gain has taken place over the area over the time. So what we have done is, in last year we have compiled some of the measured forest hotspot where we have seen the forest losses as well as forest gain all over the India using only the Indian remote sensing satellite. So here is the image of an area which is very near to your campus, that is in the Lohit district, Arunachal, like near the Teju area. A chunk of forest that is in Kharman area, that is in between 1997 and 2016, like how much area has been lost, we can clearly see from this one. So similarly, again, another hotspot is near the in between like Dimapur, near Dimapur and like this Dima Hasao area in northeast itself. Like here, you can see like a chunk of forest again clear in between 1998 and 2016, and you can also see one highway developing in this area. Another measured loss that we can see is it's the Sonitpur area near the Nameri Tiger Reserve adjoining the foothills of Arunachal and Assam. This is like the Nameri Tiger Reserve. Then if you go a little bit side, then you will have this Balupung, and from this ridges is the starting of Arunachal Pradesh. So how much forest loss has taken place in this foothill, especially these are all because of the human settlement and like cultivation purpose. Again, if you go for further extension in the along the horizontally, like along the Sonitpur area, then in Sonai, this one in Assam itself, like a measured forest loss has taken place in between 1999 and 2007. Then these are some of the forest loss or the vegetation loss which has taken place because of the hydropower project. This is the coal dam which was built in Himachal Pradesh just in 2014 and 2015. How much of the vegetation has been under water, we can easily see from the satellite images. Then another forest loss is due to the coal mining. This one is the Singrauli mining coal mine fields, how the mining has affected the area. You can see over the expand how these mines have expanded and how much losses of vegetation has taken place over the time. And some of the effect of tsunami, where we have lost land because of tsunami, we can also easily see from the satellite images. This is in between 2004 and like 2012, how much like land we have lost because of the tsunami. We can easily see from the these three satellite images. And then beside all these losses, we have also seen some measure gain in the forest area. This is the mangrove region in the Maharashtra, like in between 1998, 2001 and 2016, when people have started realizing like the importance of mangrove. People have changed their perception and given more emphasis on the plantation and like rehabilitation of mangrove area. So in between 1998 and 2016, like the mangrove forest has increased over this area. So these are some of the simple analysis which we can do, like with just by seeing the satellite images. But in order to quantify, we have to convert all these into area, or like we have to bring those into special information, and we can deduce how much area has been lost or how much area has been increased. So in order to do that, another in today's the webinar, like mostly things what I have covered is like the things which I have worked with or like which I was involved. So mostly it's all the case study and like different case study in which remote sensing or remote sensing GIS and like GPS are used for deducing the information and like how the information can be used in management or like in field of forestry and ecosystem study. So another study regarding this one, the habitat assessment was carried out in the Tawang region, that is bounding Bhutan and just nearby the China border. When I was in WII, we carried out one study regarding the blackneck crane conservation. Here, the purpose of this study was to quantify the habitat of this area. and to see how much accessible, how much like whether it is possible for them to be built in this area in connection with the conservation of black-neck crane. So if you see the right image, like this one is the study area that we have chosen, which was an important area, which was a very important area for black-neck crane. And this is the from the DEM we have derived the slope, like how the terrain of that area is, and this is the study area. So we have marked out the habitat of black-neck crane, and for the information, black-neck crane is one of the species of crane, like which is only available in the high altitude, especially in the Himalayan belt up till Mongolia, and in India we have this black-neck crane in Ladakh, and we have somewhat in Sikkim little sometimes, and like we have already seen the first black-neck crane in Arunachal was seen in the Apatani Valley, but already because of human disturbance, like this black-neck crane has already stopped visiting the area. And the only known two wintering site in Arunachal is one is the Jimitang Valley, the study area, and one is the Sangti Valley. So it was very important for us to access like the habitat of this black-neck crane and what is the possible, what may be the cause if a dam has to be built somewhere in between the black-neck crane habitat. So we have used the remote sensing information or the satellite information for mapping the habitat of this area. The first one, what I have shown is just the from the image we have understand like how the changes has take place, but in order to quantify, we have to bring that one in the GIS or the we have to do some additional work. So using the field data collected and using sentinel satellite images, we have mapped the area, total area, like where they are proposing to build the dam. So some of the important area for the black-neck crane, especially are the Hippophi area, like if you see, and some of the seasonal sandbar that you can see easily in this picture. So these are the prime habitat for the black-neck crane. So how much area is available within that study area, we have quantified that one using the satellite remote sensing and field information. So the next thing what we have done was to see the feasibility of the dam construction. So using the DEM or the digital elevation model of that area and the report that the DPR, that the detailed project report which they have submitted to WI, from there we can they have already mentioned like at how much height the dam will be built and like up to how much elevation or how much depth the water will be. That is the MDL, they say MDDL, that is the minimum drawn down level, the minimum level up till where the hydropower will maintain the water elevation for generation of hydropower. That is the meaning of MDDL. So with the, if they maintain the MDDL level, how much area will be inundated or like submerged by water, we can easily quantify using the GIS or the remote sensing or GIS information. Using the DEM using the digital elevation model data. So from there we have quantified how much area it will be submerged. So out of the total area that we have, out of the total study area, we have found out like around 40% of the area it will be submerged, and like out of those 40%, what are the different distribution or the different habitat which will be submerged underwater at the MDDL level. And then another one is the this one, full reservoir level, and how at maximum till where they will maintain the water level. So at this, how much it will be, it will affect the study area or the area. We have quantified like around 62% of the area will be submerged when they maintain the full reservoir level. And how much area, different land use and land cover, it will be submerged and how much it will be affected. We have studied this one easily using the remote sensing and GIS technology. So from this study, what we found was the, if they have to build a dam, And if they maintain the full reservoir level, then this much of the area in the blue color will be submerged, and out of that, the seasonal sandbar, which is very important for the black-necked crane habitat, 85% will be underwater. So if we have to conserve the black-necked crane habitat in the Jimitang Valley or the Tawang area, then the construction of this dam was little bit like difficult, or like the construction of dam will destroy the habitat of the black-necked crane. So this was the thing that we have done using satellite remote sensing. Then beside that, just for this in this study, we have also run some models like the FAPSIM model in order to quantify like the environmental flow, how much it is required in order to maintain the habitat of the black-necked crane. And it was worked out like around 20 QMax if the this one dam construction is done, and if they are able to maintain 20 QMax during the December, January, February month, then the habitat of black-necked crane may be somewhat what to say conserved. But it was not feasible for the company to maintain only 20 QMax, as they have to do the power generation continuously. So finally at the end, like this was a recommendation that we gave from that study. So this is one of the example how we can use the remote sensing satellite images for studying the habitat, and like how it will affect with the hydropower dam or the hydropower generation project. The another study is like, which is very strongly related to forestry application, is the use of high resolution satellite images for finding out the number of trees as well as the crown cover, because the crown cover can be a useful information when we talk about silviculture, whether the pruning operation has to be done, or like how much dense, or like the dense is the forest or the tree outside forest area. If we have to identify, then we can use the high resolution satellite images in order to do that one easily. So in this, we have taken an area like near Dehradun itself, near the Rishikesh and near Rishikesh and Haridwar. There is a reserve forest called Barkot. There we have taken a patch for a trial purpose. Like we have used the World View 2 image, satellite image. Then we have used other software like the ArcGIS, and we have used the R packages for automatically extracting the numbers of tree and finding out the crown density of this area. So for this one, this is the methodology that we use. The first thing is we use the high resolution satellite images, then we calculate the vegetation indices. Then from the vegetation indices, we can give a threshold to identify which one is forest and which one is not, which one is vegetation, which one is not. Then based on the local maxima filter, we can run the algorithm, the ITC, the individual tree crown extraction segmentation algorithm. Then we can get the full crown filter. Once we have the crown filter, in between we have also done some improvement. Besides just using this algorithm, we have find out the area, then which is the feasible area, how much crown area it can be. If it is below like 1 meter, then it is difficult for it to be a tree, and if it is like 200-300 meter crown, then it will be not feasible to be a tree. So we have put all those filter. Then we have also put another filter like the how much circular index there. We have calculated the circular index of the crown. If the shape of the crown is like somewhat coming as a rectangular or a triangle or a square, then the possibility of being a tree is little bit difficult. So we have filtered out all those just in the algorithm itself. Then we can finally get the number of trees or the crown that is present in that study area. So this is one of the example like what we have done with the different threshold. We have given like the NDVI value of 0.4 and like 0.26, 0.37, like how the crown extraction is taking place. If you see with 0.4, like the crown will be little bit of smaller area. So we have to check like which threshold works the best in our study area. In our study, we have used somewhat like 0.37 NDVI value in order to differentiate crown and like other vegetation. So this is the algorithm that we have run in ARC. Then similar thing can be seen in the ArcGIS for ease. We have done this one. You can see the crown area. You can see the parameter. You can see the index with that we have developed, whether it is circular or not. If it is perfectly one, then it means like it is circular, and towards one means like it's more circular. And if it is like less than near to zero, that means like it's not circular. So those filter we have applied, and finally we have estimated the number of the trees that is present in that study area. The actual number of trees that we have manually counted, it was 268, and using the EVI, enhanced vegetation index, the number of individual that we could have identified automatically, it was like 270. So there was a difference of like two number of trees. So there some improvement can be done in the same algorithm. We can use we can change the threshold, or we can use some other vegetation indices in order to improve this one, or we can try for more higher resolution satellite images. So similarly, we have also calculated the crown area for this total study area, like how much percentage it was. Like 15% of the area was covered by the crown, and the total area was like 18,903 meters square. And how much overshoot, undershoot, this can also be accessed easily. Another application, or like things that we have in remote sensing and GIS, is the geostatistics application. So KK Sarma sir has almost covered the biomass estimation, but this one I have taken biomass as an example, but we can apply the same technique to different variables, whatever our variable of interest is. So there are different techniques for estimation or interpolating the forest parameter that we are interested. Here we have taken the biomass as a variable. So some of the technique that is easily available in inbuilt in ArcGIS, or the commonly available remote sensing or GIS software, are the Thesian polygon. Then we have our IDW, which says the inverse distance wedges, which is given by like 1 divided by p to the power 2. Like the farther the distance, the lesser the watt is. Then we have this spline. So these are the different technique which I have used just to estimate the biomass for this whole study area, that is the barcode area. So using the Thesian polygon, we have interpolated the possible biomass. Then IDW, if we use the IDW technique, how the biomass it will be, and if we use the spline technique, how it will be. But if you see the FCC image, then the true color image, then we can easily say the biomass represented by this polygon, or by IDW, or by this spline interpolation. It's not the real picture of this biomass that will exist in the barcode forest. So further, what we have done is like we have used the kriging technique. Kriging technique is one of the geostatistical technique which uses the which exploit the special autocorrelation that exists in nature. By law of geography, what they say is like the things, everything is related to everything, but near things are more related. So the kriging, what it does is like the uses the technique of special autocorrelation in order to estimate or interpolate any given variable. Not only biomass, you can take anything, whether it is climate, whether it is temperature, or whether it is DEM, whether it is rainfall, or in mining, the kriging technique is mostly used. So this is the method that we follow in for doing the kriging in GIS domain. So here the flowchart I have given for the regression kriging. Like if we have a sample point, what we can do is directly we can go for interpolation just using kriging, whether it can be ordinary kriging, universal kriging, or co-kriging, or like probability kriging. We can directly krig that one, and we can get the output easily. Or otherwise, what we can do is we can also use the regression kriging. In regression kriging, what we do is same like the technique of regression, which we generally do for a variable with an independent variable. what we do is like we have the sample points, then we use the regression, we develop the regression between different variables. Like in this case, we have used the different vegetation indices like EVI, NDVI, and we also have run the PCA for those different band, and we have developed the regression between the biomass. Then we use that regression model or the regression equation in order to map the area. But what happened is when we develop a regression equation, there is some error that is incorporated because of the modeling error or the equation itself. So in order to improve, what we do is that whatever residual that we get from the regression equation, we use those value in those point, and we correct those error for that area. Then further, from the result that we that biomass or the estimate that we get from the regression model, we subtract that one, we subtract that from the correct one. That means like the error that we get from the kriging, we subtract that one from the regression model. Then we finally get the regression kriging results. So in this way, we can do kriging or the interpolation. So these are some of the output that we get just by using the environmental correlation or the regression equation. This is the carbon stock of the barcode area, which has been estimated. And again, this is the when we use the regression kriging, this is the estimate, but this was more of an error. The environmental correlation or the environmental regression equation was giving more representation of the carbon estimate. So other than that, we have also tested the co-kriging, and we have found out that the co-kriging, use of co-kriging method for interpolation or for estimation of carbon stock in the study area of barcode was gave the best result. So this is the variogram, what we say the for what we use for defining the special autocorrelation of an area. Here we have the nugget, then we have the range and the seal. So using those nugget, range, and seal, we get the variogram model. Then based on this model, the kriging is done. So at the end, the total amount of carbon stock that is present in the barcode was estimated to be like 2,40,797 megagram carbon, and the average carbon in that area was like 276 megagram, with an RMSE of like 58.76. We estimated the carbon stock of barcode area. So this is another case study that we have done. Then next is the forest productivity. For the same study area, we have also carried out the forest productivity study in which we use a very high-end technique called eddy governance technique or the flux tower measurement in order to find out the NE of that or the net ecosystem exchange, or what we can say the net primary productivity of a forest using the flux tower measurement. So when we get the flux tower measurement, what is the limitation is like this flux tower give us the net value or the carbon exchange between the forest and the vegetation for a footprint area that will be less than a square kilometer, or maybe maximum up to 1.5 square kilometer. So in order to upscale that one, we have to use the remote sensing or the GIS information. So this is the flux tower that we have in the barcode, which is the moist sal forest in Dehradun. Then for the upscaling of forest productivity, there are different approaches, and one of the most commonly used approach is the light use efficiency model, in which the GPP or the gross primary productivity of a forest is defined as the product of like the FPAR, that is the fraction of absorbed photosynthetically active radiation, into PAR, that is the photosynthetically active radiation, that is the incoming solar radiation, which is coming in between 0.4 to 0.7 micrometer, and EG is the realized light use efficiency. And in order to get the realized light use efficiency, what we have is the Emax, and the temperature scalar, it is multiplied with the temperature scalar, water scalar, and the P scalar. So where does the remote sensing come into roles? It is the in calculation of water scalar, in calculation of P scalar, we can use the remote sensing satellite data. Other than that, nowadays, all these climate data like the calculation T-scalar as well as the FPAR, we can easily get that one from satellite images. Especially the FPAR calculation, we can directly calculate that one using the satellite image, because FPAR can be defined as a function of the LAI, or even some people has already developed equation for deriving the FPAR using the NDVI or the EVI, which is a product of satellite remote sensing. And other product like the PAR, that is the incoming solar radiation, we can get it from globally available satellite information which is in geospatial domain. And temperature scalar also we can get the same. So this is the basic light use efficiency model which is most generally used. So some of the example are the modest GP product. They also uses the light use efficiency model, the 3GP model. They also uses light use efficiency, the CFIX, the VPM, the ECLUE, and the CASA also. All these models, they use the light use efficiency model. So we have also used the light use efficiency model for the study, but we have used little bit modification, which is for our study, we have used the P scalar and the water scalar, which was derived from the different vegetation indices. That is the LSWI, that is the land surface wetness index, which is which can be derived using the NIR and the SWIR band. So other than that, like for calculation of FPAR, remote sensing also plays an very important role when we have to define the FPAR of a forest, or the fraction, how much of the light is being absorbed by the forest. We can quantify that one using satellite remote sensing. Here, the first one is there are different methods. Some of the methods are like using the Beers-Lombard law. They have already given the equation, like where we have to just give the LAI value of the forest area and the constant, that is the K, that is the light extinction coefficient. We can get the FPAR of that forest area easily. Or otherwise, we can use the simple ratio index, or we can use the NDVI index, or we can simply use the relation that has been developed using the NDVI value. So these are some of the technique like which we can use for deriving the FPAR of a forest. So in order to do that one, what we have done is like we have field measured some of the LAI, monthly LAI of already some fixed location within the study area, and we have developed a relation between different vegetation indices in order to extrapolate, or like to map the LAI of the whole forest area. So out of those, what we have found was the use of this one very. There are 5 indices that we have attempted. Out of that, very was the most suitable index. That also in the this one linear form, it has the R square of 0.75. So we use the very index for estimation of LAI. Then once we have the LAI, what we have done is we got the LAI using the vegetation indices that we derive from the satellite remote sensing. Then further we have estimated the FPAR of those area. You can see like this is for the February, this is for June, this is for September. Similarly, the FPAR of that area or of that forest has been estimated. So using all this variable, what we have done is we have estimated the GPP of the area or the Burcoat forest on 8 days basis. So from December 3rd, 11, then like 19, like how the gross primary productivity of the forest is taking place. So if you see towards December, or like with the start of January, the GPP or the gross primary productivity of the forest, like it's a little bit like low. Than once with the starting of April, like with the flushing of new leaf, the GPP increases a little. Then in the May, and like somewhat in the May and June, here the issue is like with the optical remote sensing, there are some issue with the cloud cover also. This June 4 and August 5, the underestimation of GPP that you can see in this side are mostly due to the presence of cloud. Here in July 15 also, this is because of the cloud. Otherwise, if you see the trend, the increase in GPP value, you can see like from January till April, then in June, July, then in August, like it will increase. Then in September, like after the like late monsoon and the post monsoon season, you will see the maximum GPP of a forest, especially in the northern India. So we have estimated the GPP of this forest on a like 8 days basis and annually also, and it was validated against the flux tower or the ground measured GPP. So similarly, there is one more the easier technique that we can do for estimation of forest productivity just by using the EVI and the LST. These two are already like only the satellite derived product. So we don't have to use the other climatic parameter like the temperature or the incoming solar radiation. So we can just simply base on the EVI and the LST, that is the land surface temperature product, we can estimate the GPP of an area. So the TG model or the temperature greenness model, uh, it uses these two parameter, that is the EVI and the LST, and they are scaled based on the information that was developed by Sims ETL in 2008. Like the scale LST is given by minimum of LST divided by 30 or 2.5 minus 0.5 into LST. Whichever value is less will be used as the value of scale LST. Then the scale EVI is done simply just by subtracting 0.1 value from the actual EVI value. So once we have these two values, then we can simply these are some of the LST product of that forest, Barcode forest area. This is the true color image, then this is the FCC, then the LST product of that area. The similar thing which can be seen with the VIRS satellite, then for the modest satellite LST product also. You can see like the difference with the difference in the spatial resolution, like how pixelation is done. So we have used different technique. So how the TZ model or the temperature greenness model it works is like the LST, the land surface temperature, can be a proxy of temperature as well as the vapor deficit pressure. If you see from this graph how it relates, like the land surface temperature, which is a satellite product, and VPD, which is a ground measured one. But if you see, there is an exponential relationship between the land surface temperature and the VPD, and VPD is a very important parameter, that is the vapor deficit pressure, which control the photosynthesis of a forest or for any vegetation. And another one is the temperature. Your temperature also has a very important role in the forest, like plant physiology. Like it has both the limiting, like if it is too low or if it is too high, then there will be some reduction or like stoppage in the plant production. And if it is optimum, then the plant production will be more in that time. So LST can be simply related directly with the plant physiology or the plant productivity. That's why if using the TG model, it is possible for us in order to in quantifying the forest productivity of an area. So simply, if you see, this is how we have done the scaling of the LST for that barcode area, and how we have derived the different productivity of on 8 days basis for that study area using just only the EVI and the scale LST. And these and next is the same thing as P.K. Joshi sir has already mentioned in the starting, and on the first day, like nowadays we don't need any software like commercial software, or we don't have to have a very high computing machine in order to work on a large scale or in remote sensing data. This is the study that we have done using the temperature greenness model, and we have estimated the gross primary productivity for the foothills of whole Himalaya, like starting from Jammu and Kashmir till then Himachal, then the Uttarakhand region. Also, we have estimated the GPP for this area using the TG model in the Google Earth engine itself. So if you see, these are some of the images, that is the EVI value of like January, April and October, then the same like the LST value of January, April and October from the Google Earth image, from the Google Earth engine that we have derived. Then similarly, using this EVI and LST, we have estimated the GPP of the whole region, that is the foothills area. Like you can see how it changes, like August, September, October, November and December, how the GPP changes over monthly, and like how it has changed, how it has increased, or like how what is the trend of productivity in the foothills of Himalaya, both in the most deciduous forest and the dry deciduous forest. Then another case study that we have done is the utility of satellite time series satellite data in classification, or like in mapping of different vegetation type. So what we have done is we have used the NDVI Landsat 8 NDVI data from 2013 till 2019. Then we have used the Fourier transformation. Then we have decomposed that one into sine component, cos component, the mean component. Then we have others like the DEM, the aspect, the temperature, and the precipitation, all in the raster format or in the geospatial format. Then we have stacked that one. Then using the training set, the field points. Then we have used the random forest classification, and we have mapped the plant functional type of a sample study area. So this was also carried out using the in the Google, this one art engine itself. Like we have so that we don't need to download this amount of data, so we have just run the uh, algorithm in the Google Earth engine itself. So if you see here, like from the Google Earth, in the Google Earth engine itself, with some practice, what we can do is we can just write the code, and like you can get like what is the range in that particular pixel or the particular area that you want. You can get the plot itself. Then the satellite image will be displayed in this down section itself. So particularly for the students community that are present today, like they can explore in this domain, and like they can see, because if you go and check out in the Google Earth engine itself, there are plenty of number of examples they have already given for us to learn, and we can slowly develop, and like we can enhance further also. So I would advise like all the students to just go and check out the different examples, how to calculate the NDVI or the EVI, and how to map the different wetland, all these things, that it can be done easily in the Google Earth engine itself. So from the Google Earth engine, we have used the time series data in order to quantify different plant functional type. So if you see the time series data, oh, okay, like just I want to add something. Like what we have seen before is like we have used only one time satellite image in order to derive information for a particular area. What a case study what I have shown before, but in this, like we are taking advantage of the time series data in order to improve our classification, in order to improve like capture like what are the different phenology. So based on the phenology, we can classify all those different plant functional type. So if you just see in 2000 from 2013 to 2019 itself, like how the NDVI value changes. Like this is the this one transform the Fourier transformation, or the uh, fitting that we have done, and this is the actual NDVI. And if you see the mean value where it ranges for an evergreen needle leaf forest, what it happens is like the NDVI mean NDVI almost ranges between near zero point 0.4, and if you see for the broadleaf, it is little bit higher than the needle leaf forest. The NDVI value is around zero point 0.6. So in this way, you can differentiate. You will be able to differentiate like needle leaf from the broadleaf forest. Similarly, again, if you go for the dry deciduous forest, like how the pattern of the NDVI it changes over season and over time, you can analyze from this one. In case of urban area, like as there is no vegetation present, then the NDVI of that area remains almost flat, but it was little bit beyond like zero point 0.1. So again, for the water, if you see the NDVI, it almost ranges like it stays near like minus zero point 0.2, and for the snow it's like zero point 0.1. So in this way, we can easily segregate different plant functional type or the land use type based on the time series information also. Because in most of the case, what happen is if we use only one time supply data in our classification system, and if you are going to use like NDVI or an EVI index, or any other vegetation indices just to classify agriculture and forest, then sometime there may be some misclassification also based on the time of the year or the season of the supplied image. Suppose if there is presence of agriculture, like if there is like growth, or like if there is fallow period, then if there is like deciduous nature of forest, it may be a little bit difficult. So when we use a time series information for a year or for 5 years, then we can easily differentiate like, okay, deciduous forest, how it works. Like for an evergreen forest, there will be always some presence of NDVI, or the NDVI will be almost more or less same, remain constant. But in case of dry deciduous forest, what it happens is like maybe in the January February season, like the NDVI value will be very less than in with the onset of monsoon, like July to October, November, the NDVI will be high. So in those way we can segregate these different type of vegetation. So in this way, we have mapped the different plant functional type of our study area using the time series NDVI in the Google Earth engine itself, using the Fourier transformation and some others variables like the temperature, then the temperature, the DEM, then the SPAC and slope also. So okay, this one I think mostly like Dr. Manoj has already covered like the forest fire aspect in his in his presentation, but here is I have put it. So here the difference is little bit like what I have done is the use of satellite data, like in order to map the vulnerable or the forest fire risk area. So should I continue with this one, or like should I skip this one? Kindly give your opinion. Hello, can anyone hear me?
Am I audible to you, Dr.
Yeah,
Patnaik? Hello.
yeah. I can hear
Sir,
you.
you continue. You continue.
Okay, I'll just
Okay. This forest fire risk assessment also you continue.
Ha. So forest fire risk, for forest fire risk assessment, what Dr. Manoj has already covered is mostly about the forest fire like alert system, which uses the MODIS and the VIRS data for the near real-time prediction of forest fire or near real-time detection of forest fire. But in this, like what I have used is what I've done, what we are doing here is like the potential like forest fire risk area, like which are the vulnerable area or the which area has to be taken care of. So in order to do this one, what we need to do is like we have to first understand the forest fire, like what are the different parameters or the factors that affect the forest fire. So some of them are the vegetation type based on the vegetation, whether it is pine or the dry deciduous forest or the evergreen forest, like the possibility of fire occurring, it depends. Then the climatic factor also, the temperature, the rainfall, like the wind speed and the wind direction also, these are some of the factors which influence the forest fire. Then the physiographic factor, that the altitude aspect and the slope also. Then the edaphic factor, like the soil also, it also have an influence on the forest fire. Then the distance from the road, like how far it is, like because mostly in India what we have seen, that the forest fire occurs 95%, more than 95% of the forest fire in India are the man-made forest fire. So we have to consider this, especially the last two component, that is the distance from the forest and the vicinity from the settlement, when we have to map the possible risk area for forest fire. So all this information that is listed here, we can get that one in the geospatial format. So once we have that one in the raster or the geospatial data, then what we can do is, based on our idea, we can further class those information into categories, like which are more vulnerable. Suppose if we take distance as a parameter, then the nearer the distance, then the more possibility of that area having forest fire is more. Like the more the vicinity, then suppose say in the vegetation type also, if we have the pine forest, then the chances of forest fire in that area is more. Similarly, if there is higher slope, or then the chances of forest fire is also more. So in those way, we have to we have to give the priority based on our idea. Then we can further at the end we can map the possible like the vulnerable or the risk area. So this was the methodology that we have adopted. So we have used the topography like the slope aspect and the elevation from the Sentinel-2. We have used the NDVI, then the NDWI in order to capture the moisture regime of that area. Then we have also used the LST for the from the VIRS and the modest VIRS and Lancet 8 data for the thermal regime. Then we have used the Lancet Sentinel-2 for mapping the vegetation type in order to quantify the what type of fuel or what type of vegetation is present there. Then we put the human influence, that is road, settlement, and stream. Then at the end we put all those. Then we parameterize that one like based on our knowledge, like which parameter and which index has more influence on the forest fire. Then we do the multi-criteria analysis, or like we can simply do the AHP, that is analytical hierarchical process. Then at the end we can get the forest fire risk donation. So in this way, like we have mapped the vegetation of the Dehradun district. Then the based on the vegetation type, we have made like different whether which vegetation type has are more prone to forest, then which are less prone to forest. We have classified that one into low, very low, then moderate, then high. Similarly, we have estimated, we have calculated the slope, then the slope index from the slope. Based on the slope, then we have calculated the slope index. Then we have aspect, then elevation, then we have generated the index for that one. Then the based on the road and settlement, we have also developed the index by index or the ranking we have done by giving the buffer. Simply we can use the buffer tool in order to rank like which are the area which are more prone to forest fire and which are not. Then from the stream, then the land surface temperature, we have also met the index for that one. Then from for the moisture regime, like we have used the NDVI as well as the NDWI. Then we have developed the index for that one. Then we have used the AHP process, AHP method for giving the priority. And we have developed the final equation and vertex matrix and the equation for accessing which are the vulnerable area to forest fire. So these are the vulnerable forest area of Dehradun, like the based on the ranking, like we have classified that one into very highly prone forests, which are forests which are highly prone to fire, then high, then low, all those like, and we have overlay with the forest fire point, which is disseminated by this FSI as well as by NASA itself. So we have checked and cross verify like where the forest fire occur, and like the forest fire vulnerability map that we have prepared has a very strong agreement with the fire points that was detected by this one FSI, this one MODIS as well as VIRS in real time forest fire points. So these are some of the studies like which I was involved like part of it. So some of the other satellite sensor like which are coming up, which are already in process, like which we can use for ecosystem study, are like the OCO2. Like from OCO2 we can directly, using satellite sensor, what they are doing is we can directly estimate how much carbon contained in the atmosphere itself. The total columnar carbon can be estimated using the OCO2 carbon observatory satellite. Then from the OCO2 itself, nowadays there is another product called SIF, that is the sun-induced fluorescence. From the sun-induced fluorescence, it's a proxy or an indicator of like plant photosynthesis. Suppose at the time during the time of photosynthesis, what it happens is like it emits some certain amount of light from the plant or from the chloroplast itself. So the satellite, what it does is it try to captures those emitting that fluorescence. So if we are able to capture that one, then we can directly relate that one with the amount of photosynthesis that is taking place by in that plan, whether it can be a forest ecosystem or it can be a agro-based ecosystem. But once we have that one, then we can, it will be a very useful information when we are studying the forest productivity or agriculture productivity. The another sensor is the eco stress, which is like part of the international space station itself. Like we have these eco stress data from the eco stress, or they give readily product like the ESI, that is the ecosystem stress index, which give us like how much stress that ecosystem is experiencing based on the uh, thermal radiation that the sensor receive. Like the actual algorithm is based on like the based on the thermal sensor. They calculate the PET, the potential evapotranspiration, and the actual evapotranspiration. So if they take the ratio of that one, then it will give the ESI, that is the ecosystem stress. Then another sensor is the GOSET. From GOSET also, like they are monitoring the methane as well as the CO2. Then we have newly launched the Prisma, which is a hyperspectral satellite sensor from the Italian space agency. Then one of the coming up mission is the NISAR mission, which is the joint NASA and ISRO's SAR mission, like which will be starting soon, which has the S band and the L band sensor for particularly estimation or like for the ecosystem study. So these are some of the like some have already, some are already available. The OCO2 data are readily available. We can download that one, in whether it in form of like CO2, we can get the information. Then even the sun induced fluorescence, that is the SIF, the product is available. Then the eco stress also we can easily download and see how the stress, if we are studying the ecosystem stress for an agriculture or a forest, we can use this one. Then the GOSET also is available. Then Prisma, we can download the data, it's freely available. Then NISA, it is going to come up soon. So these are some of the newly coming up, or like which are started in field of ecosystem study. So this is finally the last one. Like I have extracted some of the CO2 measurement that the CO2 is giving for the northeastern region of India. Like you can see, like in some a few pockets of Assam, like there is like CO2 ppm is more than like 415, and like other portion like it has less than like it is around 405 to 410, and few pockets like near boundary in China side, in Myanmar also, like the carbon concentration is a little bit higher. So these are some of the things that we can do from the satellite remote sensing. So I think with this, I have presented mostly like the things that which satellite remote sensing can be used for ecosystem study as well as for forestry.
Okay, thank you, Dr. Taibang. So you have a very good presentation. As we have talked earlier regarding that, you are the last speaker. So you have already summarized all the aspects of application of geospatial technology in forestry. So you have also covered that forest risk assessment. Anyhow, forest fire risk assessment. So some of the new sensors regarding you have also highlighted. So thank you very much. So now, before I have some questions I may ask later on, but I now give a chance to our participants. If you have any question, you please ask Dr. Taibang online, or you can go to the chat box and you share your questions, queries. So you can just okay. So please you ask some of the queries in chat box also. We can read here, or I can have some questions later on. Okay, thank you very much. Chat box.
Or some more technique, like if you want to know, then I can just brief some of the things that we
Okay,
do.
Dr. Taibang, you can also explain about the techniques.
Like some
Actually,
of
what are
the like
the, just you please, can you summarize something. So, for example, our forestry students, they
Hmm.
are also in MSc and PhD.
Yeah.
So, and also UG, they don't need so much application part. So
Uh,
they want some fundamentals, but as far as the various softwares are, what are the free softwares you can tell, and what are the common softwares used
okay.
in our India, in our institute, and just to please highlight.
Hmm. I'll do that one. Just before that, like for those like those who are doing BSc forestry or like who have done their MSc, what I would say is like IARS provide opportunity for the students like to do their studies in remote sensing, in, whether it can be a PG diploma, which is like for 9 months, and like we have MSc degree, which is in collaboration with the ITC Netherlands, like which is a 2 years course, and like you have to stay in Netherlands for 3 months for in order to complete your study. Then we have our MTech program also, where you'll be taught for 9 months, and like for another 1 year you have to carry out research in order to complete your MTech degree. So those are some of the things that we provide in IARS. And some of the commonly freely software that we can use is the QGIS. QGIS is one of the most common software that we use, like which is readily available for free. And other than that, what I would suggest is like nowadays, if we have little bit experience, or like if you are not scared of computer, I think like you should not be, because me being a BSc forestry student, I have also done BSc forestry, then MSc forestry. I have somehow managed to use my computer up to some level, like where I can use all those software as well as the programming skill, just to get my desired output. So I think in our package also, lot of packages are available. Freely packages are available. You have to just download that one and just understand a little, and you can do lot more than what I have shown in my PPT. And other some of the free site which you can access is the Bhuvan, also is one of the site which is hosted by NRSC Hyderabad. For India, like you can easily download some freely available data. Then you have already the web portal. You can see what are different product that is available. Then from the other international, you have the Copernicus, where you can download your Sentinel-2 data as well as the Sentinel-1 SAR data. Then you have your US GIS. Then you have your search art data, where you can freely download the Modis data, Modis product, the Lancet data, then the Sentinel, all these freely available product. Then Prisma also, you can check, it is already freely available. You can download that one also.
So, Raja will conclude. Hello. So now, dear participants and our honorable speaker, so now we have come to an end to the seminar. So now Dr. Taiwan, hello.
Yes, yes, sir.
So actually, our students are going to FRI also for the higher studies,
Yeah.
and you have told some of the programs are running in IRS.
Huh.
So whether they are the paid programs,
Mostly it's paid program. Otherwise, in IRS,
are they,
we also have this EduSet program also, where they can learn online freely, and if they pass the exam, they will be issued a certificate, but they have to clear an exam. That one is for free.
okay, that is a that is a good information for our students. Students, please note all these things. So, if possible, also we have the mail ID of Dr. Taibang. You may contact him
Yeah, you
as
can
a
contact
senior
with
of
her.
yours. So we are also fortunate that he is a man from Manipur. So we have many students from Manipur also in forestry. So anyhow, so now we have come to an end to this this seminar. So now I would request Dr. Aja to give the formal vote of thanks for the seminar. Later on, can I summarize some of that? Okay. Now I am summarizing what are the different sessions and different aspects we have already done. So now in this 3 days webinar, So we have 6 speakers throughout the country. So among the first session was started on 26th November 2020. So in the first session, our inaugural lecture was by our Professor P.K. Joshi, who has delivered a lecture. One, So who has delivered a lecture on that managing forest and forest resources, a geospatial perspective. So he has given a very excellent lecture. So covering almost all the topics of application of geospatial technology in forestry, and also he has mentioned about the UAV and how the drones are now used to get some resolutions up to centimeter level. So the next speaker of that day was Dr. P.K. Singh, the director, Geological Survey of India, Lucknow. So he has mentioned about the principles of remote sensing and the application in forestry. So as a geologist also, he has delivered a good lecture on the topic. So related to this seminar title. So now the second day starts with the speaker, that is on 27th November 2020. So Dr. K.K. Sharma, who is the scientist SG from NESAC, Department of Space, Government of India, Meghalaya. So he has delivered a lecture on forest growing stock estimation through geospatial technology. So he has also given very valuable and very important case studies regarding the application of remote sensing in forest growing stock estimation. So I expect that our participants have got a lot of information from him. So he has also giving one information regarding the relation what FSI, Forest Service of India, is doing in the large scale in state level in but in NESAC or NESAC they are also doing in the northeastern states in the block level, village level work. So they are doing a good work. So now the next speaker was Dr. Ishwar Chandra Das, scientist SG and head SHD, National Remote Sensing Center, ISRO, Balanagar, Hyderabad. So he has given a good presentation on the mapping of spring sets and spring set rejuvenation for sustainable water resource management using geospatial technologies in Indian Himalayas. So he has mentioned about the why the springs are drying. So how to rejuvenate their catchment areas so that the springs will produce water throughout the year. So so this can be done by having a deep study on the geological perspective of the particular area. So we got some clarification from him that why we are not going to get we are not usually getting the groundwater near to a river. So he explained very nicely, giving a case study of Mithun in Nagaland Institute. He has come here there to and visited and make a survey. So now our ISRO and in collaboration with the state remote sensing centers, they are preparing the groundwater prospect maps, which is very helpful for the state water resource department to get the locations of your groundwater areas where we can, if we'll go for a borewell, so how can you do? And he has also given the example of Netherlands, where they're having only 650 millimeter of annual rainfall, but they're managing well to their water resources. So we can have a lot of information. Then today's speaker was the last day, Dr. Manoj Kumar, who is scientist and in charge of GIS Center of IT and GIS Discipline, Forest Research Institute, Dehradun. Brilliantly, he has prepared the lecture very nicely. Lot of informations we could know from his deliberation. So our students and participants have got a lot of information. Thank you, Dr. Manoj Kumar, for his nice presentation. So he has delivered a lecture on forest fire monitoring, mapping, change detection by geospatial technology. Also, he has mentioned about how our forest fire is being managed by the forest department and by community participation of all the villages, particular area. So nicely presentation. Then our last speaker was Dr. Taibang Watham from IRS Dehradun. So he has also given a topic on an overview of remote sensing and GIS application in forestry. So nicely explained some of the important case studies of application of geospatial technology. So he has also mentioned about the scope of forestry students in IIS Dehradun. So thank you all the speakers. I thank on the behalf of the organizing committee that all the speakers have given, in spite of his busy schedule, regular office work, they have given us some time to interact with the participants, mainly students, scientists and faculties. So I think we have been benefited much from these lectures. Thank you all. So now I request our Associate Nodal Officer of IDP NAHEP, Dr. P. Raja, so to formally give a vote of thanks on the behalf of this seminar. Dr. Raja, please.
Mouse for your nice presentation. And first of all, I would like to thank our DI, Director of Instruction, Dr. S. Basanta Singh, who is a PI of this project. And we have all the 6 constituents having this IDP NAHE project. It is ICR World Bank funded project. And we are having this one for the as an institutional development plan, National Higher Education, National Agriculture Higher Education Program. So under his guidance, we were doing this one, and we have a different nodal officer. Nodal officers are dean, and in charge of this project is associate nodal officer and myself. So I thank Basanta Singh sir, and also I would like to thank our nodal officer, Dr. B.N. Hazarika, for his support and guidance to conduct this online trainings, webinars, and workshop for the benefit of the students. And also, I would like to thank Dr. Saroj Kumar Patnaik, being organizing secretary of this 18th webinar. And successfully, he could contact a lot of resource person from across India. And it was one of the subject students need more information on geospatial applications like GIS and many other. And all the resource persons, like he brought him, and so it is a benefit for the students. I would like to congratulate him and thank him for bringing many resource person and actively involving the students to participate in this program. And finally, I would like to thank all our project staff who are working day and night for the success of the program. I would like to thank our SRF. I would like to thank our other project staff. First of all, SRF and Nuni Thaing, and office secretary come accountant, Monisa Melong, and also Takib Talo, supporting staff. And also I would like to thank all the committee members who are helping for the success of this program. And finally, all the participants, without you, it would not be not successful. And I really thank, I understand that nowadays in Arunachal, we have a lot of, electricity problem and heavy wind, and due to which we are streamlining on the YouTube, and later on you can watch and you can get the benefit of it. And I also thank you for all of you, all the resource person. I thank you everyone for your time for your resources, and your deliberations were very excellent, and we have note of it. Even the students, they can take notes or collecting the information from the YouTube. And thank you so much. And finally, dear participant, I would like to say that you must attend one quiz, and within short notification we will send you. Today we will send all the quiz link to you, and please watch once again. Maybe tomorrow, or I think on 1st or 2nd, we will conduct this quiz, and whoever attempt that quiz will get the certificate, and only registered participant we will send to them. So take part in that, and attempt that quiz as well as a feedback form, and finally you will get the certificate. Thank you once again, and thank you one and all. Thank you, Taibang sir, and I'll stop here.